Now, Ethernet originally started as 10 base 2 and 10 base 5. These were called ThinNet and ThickNet, respectively. Originally, Ethernet was a coaxial cable, used a single coaxial cable that ran from computer to computer, one after the other, and they shared a single physical bus, and that bus was the coaxial cable. 10 base 2 had a maximum cable length limit of 185 meters, and 10 base 5 ThickNet had a length of 500 meters as its limit. And if you wanted to go beyond that, you had to use some form of a repeater. Now, eventually, as technology developed, they started to implement 10 base T. 10 base T used twisted pair cables instead of a single shared coaxial bus. They still, however, by using hubs, formed a single physical bus in terms of the actual wiring. And I'll have a diagram for that on the next slide, so hopefully you can get an idea of what's going on. Now, Ethernet lowered the limit from 185 to 100 meters. However, you don't have to run cables from one computer to the next computer to the next computer anymore. You can actually connect all of these computers to a central device, in this case a hub. And so this allowed for a much more flexible network topology design and allowed people to basically push the limits of the Ethernet technology. Later on, we saw the advent of 100 base TX, known as Fast Ethernet, and 1000 base T, known as Gigabit Ethernet. We've also seen now 10 gig base T, 10 gigabit Ethernet, which is still kind of a developing technology, and there are also some other higher level technologies now, even for 100 gig Ethernet. So 10 base 2 and 10 base 5, this is the idea behind this diagram, is to sort of give you an indication of how it works. In this case, we have a coaxial wire that runs between the network cards, so you are going not to a central device but from one computer to the next. And so this coaxial cable would snake through a building going between computers, and as you know from the previous slide, the maximum length depended on the type of coax cable being used, basically the thickness of the cable. There were 50 ohm terminators used on the ends of the cable that basically fed the current back into the into the center of the coax cable, so that we didn't have to worry about grounding problems. Now, the idea behind this was that if one of these cards raised voltage on this coax cable, all of the other cards would see the raised voltage, and so in this way we've established a single shared bus between all of these devices. Now, when it came to twisted pairs, and I've kind of created a diagram here, this isn't strictly speaking true, but this is the best analogy I could think of. So you can see each of these computers has a single transmit and receive pair, and I represented these by two individual wires coming from each computer. Now, you'll notice all four of these particular computers are connected to a hub, and basically, in essence, what a hub does is it connects the transmit of one computer to the receive pin of another. And in essence, if you trace these transmit and receive pairs from one computer to the next computer to the next computer, it forms one big loop that is one shared physical bus, much in the same way that the original coaxial cable did. So when you're connecting several computers to a hub, the actual physical dependency of, raising a single line's voltage is not that much different. So I encourage you, again, think of Ethernet, the original Ethernet technology, as a single shared bus. So on this slide, you can see an example of the different cables used by Ethernet. Originally 10 base 5 and 10 base 2, which are there on the top, ThickNet and ThinNet. You can see that center coaxial pin, which was used to raise or lower voltages, and that had to be shielded by, in the case of the bottom one, a copper, or in the top one it looks like some sort of conductive aluminum, probably weave, that shielded the cable from interference. And so that was why we had these limitations on the lengths of cables being run. Now on the bottom you have 10 base T, which you'll notice is relatively unshielded, but we have these twisted pairs, and basically how these pairs work on each pair, there's a light wire and a dark wire. And the light wire carries current in one direction, and the dark wire carries current in the other direction. And so because of this twisting, this electromagnetic coupling, we end up basically canceling out all of the interference from one wire to another. And so by doing this, we can transmit these fairly relatively weak DC signals over very long distances, and because of the twists, basically the number of twists in the wire, they end up canceling each other out, and so we get the 100-meter limitation. So this is an example of the wiring used in 10 base T, that is regular Ethernet, and 100 base TX, that's fast Ethernet systems. You can see the top two pins, pins 1 and 2, are used for transmit, positive and negative. Again, these two wires are twisted together to eliminate the interference that could be caused by external sources, to basically reinforce each other. Now you can see the green-white wire there and the green-dark wire there. The green-white wire is on pin 3 and the green-dark wire is on pin 6. Basically, the reason that it skips around like this is to avoid interference between pairs. So what happens is pins 1 and 2 are used for transmission, and pins 3 and 6 are used for reception. This is by what I would consider to be a transmit device. More on that here in the next slide. So here's the idea behind pair use. Again, equipment at layer 3 plus, I will consider these types of devices to be what I would call transmit devices. These are devices that are used to basically originate packets. So these devices are going to transmit on pins 1 and 2 and receive on pins 3 and 6. Now, obviously, if you want to connect these devices to, say, a switch or a hub, you'll need to make sure that the device on the other end, that is the switch or the hub, is receiving on pins 1 and 2 and transmitting on pins 3 and 6. Otherwise, you wouldn't be able to communicate to it. So that's exactly the behavior we see. And so equipment on layers 1 or 2 will basically switch the transmitting and receiving pairs back and forth. So basically, you have the router transmitting on pins 1 and 2, and the switch receiving on pins 1 and 2, which makes sense. That way the switch can receive the data being transmitted by that router. Now here's the deal. What if we want to go from, for example, a computer directly to a router? Well, both of these devices transmit on pairs 1 and 2, and receive on pins 3 and 6, so if they both try to transmit, if either one tries to transmit, they'll both be raising voltages on the same line, and pins 3 and 6 will go unused, just be dead space. So what we have to do is we have to basically make what's called a crossover cable. What this crossover cable does is it takes pins 1 and 2 on one side of the wire and actually rewires them on the other side of the cable to pins 3 and 6. This way we can connect two devices that are the same type. Again, I consider the top type a transmit type device and the second type a receive type device. So finally we get to a modern point. Now you may be asking yourself right now, well, I've connected some of these devices together without any issues at all. I haven't had to use a crossover cable. What's all this business about crossover? And the answer to your question is most devices will actually now do auto detection, where they'll detect what lines are being used for transmitting and receiving and try to switch their pins accordingly. This is called auto MDIX, auto MDIX. And basically this is a very, very useful feature that I see it implemented on almost all new devices. Some of the switches that you'll be working with in your lab may not support auto MDIX, so you should be very, very careful and try to use crossover cables accordingly. Now you may be asking, what are the real-world applications of this? Not a whole lot, but for the CCNA exam, you'll be required to know what devices to go, you'll be required to know what types of cables are used between two devices. For example, they may give you a diagram with several switches and routers and so forth, and they'll ask you what type of cable is needed between, for example, router A and switch B, and you'll have to know. In this case, it would be a straight-through cable. So now we get to discuss some of the later developments associated with Ethernet. We've already talked a bit about 100 base TX, or fast Ethernet. As you saw on the diagram, it actually uses the same two pairs that Ethernet uses. However, because of the higher frequency Ethernet, which typically uses Cat3, fast Ethernet requires Cat5 or higher. Again, this is because of the higher frequency in the cable. Full duplex we'll talk more about once we actually run into switching. But basically the idea is that if there are only two devices on an Ethernet segment, there are only two devices using the transmit and receive pairs, and so we don't have to worry about more than one device talking at the same time. As a result, the devices can transmit and receive at the same time. This would be like you and me holding a conversation with both of us talking, and each of us would be able to understand the other one completely without having to stop talking ourselves. Kind of an impossibility in most conversational situations. Finally, we have Gigabit Ethernet, which 1000 base T uses all four pairs. There was actually another Ethernet standard calls 1000 base TX. 1000 base TX actually used two pairs much in the same way that 100 base TX did. However, it required a Cat6 or higher cable, and so because of the expense of a Cat6 cable, it didn't take off. It was very, very unpopular because people would have to recable, and a lot of them already had Cat5 cables in place, so 1000 base T ended up winning. However, like I said, it requires the use of all four pairs in the line. Finally, we have 10 gigabit Ethernet, which basically takes gigabit Ethernet and raises the frequency. So again, with that raise in frequency, we have a raise in the category rating for the cable. In this case, we need Cat6A or higher. Ethernet addressing is done with what we call a media access control address, and effectively this is also called a burned-in address. This address is 48 bits long and has two portions. The first 24 bits, that is the first 3 bytes of the address, are called the Organizationally Unique Identifier, the OUI, and the OUI refers to who made the hardware. Most manufacturers have a specific set or maybe a single organizationally unique identifier that they put on the MAC address when they make their equipment. And so, as you're doing packet captures, you may be looking at these devices' different MAC address, and it's actually possible to identify, just by looking at the MAC address, the manufacturer of the network card for that device. For example, if you're looking on a network and you happen to see a certain prefix, you may say, oh, well, that's a Apple MacBook Air or something like that. And so by just looking at that first half, you can tell the manufacturer. The second part is assigned individually by the vendor. I actually saw a list of this the other day. I believe Cisco owns about 20 or so of these organizationally unique identifiers. There are a few special MAC addresses that you should keep in mind. If we set every single bit in the MAC address to 1s, then that's represented by all Fs in hexadecimal, we get what's called the broadcast address. Now, the IP, or rather an Ethernet broadcast, is sent to all devices that share the same local link. There are other addresses that use IPv4 and IPv6 multicast, and you can see 01005E there for IPv4 and 333300 for IPv6. MAC addresses are ideally globally unique. Now, with a 48-bit address, obviously we're limited to 2 to the 48th power addresses. Now, that's quite a few addresses, but with the ever-expanding number of devices being added to networks, it's inevitable that we'll have a repeat MAC address somewhere. As long as these two MAC addresses, these repeat MAC addresses, do not reside on the same local link, there are no problems. Again, these MAC addresses are ideally globally unique, but really locally is the only significance that you need to worry about.